In this video, I'm going to talk about the second part of the inverse Laplace transform. So in the previous video, I talked about how do we find the inverse Laplace transform of a function y sub s given by f of s divided by g sub s. So here fs and gs, they are both polynomials with respect to the variable s. So the goal is we're trying to figure out what's the inverse of a Laplace transform of ys, which is represented by y sub t. Okay. So the main approach we're going to use to find the inverse Laplace transform is called partial fractional expansion or partial fractional decomposition. So in the previous video, I talked about the case one. How do we address the inverse Laplace transform problem for the first case? Meaning that when we have the ys has real and distinct poles. Okay, so when this also means when the ys has real and distinct poles. In other words, if we set gs to be 0, we can find the solution. Let's say the solution be given by minus lambda I, minus lambda 1, minus lambda 2, minus lambda n. So those ones, they are all real. Lambda i's are all real and distinct, which means they're different. Okay. And also we assume that the degree of fs is less than degree of gs. So the degree of fs and gs are defined by the highest power of s in fs and gs with non-zero coefficients. So that's the definition of a degree. Okay, and these two conditions. Okay, of course I talk about when the degree is greater than or equal to 2 degrees. A degree of fs is greater than or equal to degree of g sub s. There's a way we can simplify the whole process, and it still boils down to the computation of the inverse Laplace transform of ys when the degree of fs is less than degree of gs. Okay, please check my previous video about how to address. Okay, so if you have degree fs is greater than or equal to degree g sub s. So in my previous video, you can check how we address those issues. Okay, so under this two assumptions. One is the ys has distinct and real poles. In other words, gs can be written sort of as s plus lambda 1 times s plus lambda 2 until s plus lambda n. Okay, so I can write this g sub s. I can decompose this y sub s as a1 plus s plus lambda 1 plus a2 divided by s plus lambda 2 plus so on and so forth plus an divided by s plus lambda n. Okay, and this is a way we can decompose ys. So for each of this term over here, the reason we do the decomposition because each term, its inverse is fairly easy to figure out. Okay, so in particular, those unknown parameters a1, a2, and an, they are computed by this. So each of these ai's is computed by fs and gs. So the original y, this is also original y of s time s plus lambda I. Okay, for the ai. So we time s plus lambda I, and then we get a product basically, and then we evaluate as s equal to minus lambda I. In other words, we set s plus lambda I to be 0. Okay, you go back over here. That's how you figure out the ai. Once you do that, we can figure out all the ai's. Then the inverse Laplace transform. Okay, this is L inverse y sub s is given by yt, which is just a1 e minus lambda 1 t plus a2 e minus lambda 2t plus so on and so forth until an plus e minus lambda nt. So pay attention to here. So we have here is a minus sign. Okay, it's not a positive sign. Okay, so that's the way we can figure out the first case. Okay, so when the gs, when the ys has real and distinct poles, and the degree of fs is less than degree of gs. Okay, this is case 1. So today I'm going to focus on case 2, when we have complex conjugate poles. Okay, which means if I set gs to be 0, okay, so I get the solution of s to be, let's say, for example, somehow like that, a plus let me see, a1 plus a2 minus a2 times j. So this j is square root of -1. So you have some complex conjugate pose. Okay. Here we also assume that the degree of fs is less than degree of gs. Okay. So in other words, we still have, for example, if we do have s, fs is s plus 1. So the degree of this guy is the degree of fs is 1. So g sub s, let's say for example s squared plus 2s plus 1. Let's do another one. Is 2s plus 2, for example. So the degree of g sub s is 2. So it satisfies this property. Now we try to figure out, hey, how do we figure out the inverse Laplace transform? Okay, before talking about the technical approach in a more detailed or general solution, let's talk about an example to see how can figure out a solution. Okay, so let's say if I give you ys, which is given by 2s plus 12 divided by s squared plus 2s plus 5. Okay, that's my, so you can sort of view this top one, this guy as my f of s. Okay, like I mentioned with fs, so this is my g sub s. Okay, so let's first check the pose, okay, of ys. In other words, we set gs to be 0. Okay, if we find the solution, so s guy, this is set to be 0, which means I have s squared plus 2s plus 5 equals 0. So the solution, figure the solution is just given by -1 plus minus 2i. Okay, so we have complex conjugate pose. Okay, so this is the general approach you're going to solve the problem, okay? If we have a complex conjugate pose, we have step 1 is to write gs. So step 1 is to write gs as s plus a squared plus b squared. Okay, this is the form, okay? So for the previous example, we have gs is s squared plus 2s plus 5. Okay, this is for gs, okay? So the g sub s here is s squared plus 2s plus 5. So this one can be written as s plus 1 squared plus 2 squared. Okay, the key concept you can sort of see, this is s squared plus 2s, right? I want to do something, right? Because I want to make it a square. You basically say this is any number. This is b, for example. You just do, this is b divided by 1, 2, you get squared, right? Because that will get the s plus b over 2 squared. Okay, right? So this is whatever value you have over here, you just divide by 2, you take a square. Okay, which means if this is 2, just a 2 divided by 2 is a 1 squared. Okay, you add on 1 squared, right? Of course, you have to minus b to minus 2 squared. So this b is 2. Okay, this b is 2 and plus 5, because this is just 1. Okay, because b is 2, 2 divided by 2 is 1, 1 squared is 1. This is also 1. That's why I have s squared plus 2s plus 1. So this is s squared plus 2s plus 1. This is s squared, s plus 1 squared. This is 5 minus 1 is 4. That's why I have this. And 4, of course, is 2 squared. Okay, so we have s plus 1 squared plus 2 squared. Okay, this first one is right, do this. The second one is we write the fs as, so this is for the denominator. Okay, for the numerator, we write fs as c time, okay, c time s plus a plus d time b. Okay, so this a is whatever we already figured out. This is the number we have. This is a, right? Of course, this is b. So it's c times s plus a plus d times b. This is what I write fs as. Okay, so here fs is 2s plus 12, right? So I have to write it. Okay, let's do it here. So 2s plus 12. So I have to write this one as something times s plus a here is 1 plus db here is 2, right, basically. Okay, so because this one must match, you have 2s over here, so we must have c is 2, right? Otherwise it won't be equal, right? And once we have c is 2, so c times 1, this become 2s plus 1, 2 plus 2, okay? So here is 2s plus 12, so I remaining part, this guy has to be equal to 10s, right? So I have a 10, sorry. So I have d should be 5, okay? So I have 2 times s plus 1 plus 5 times 2, okay? This is step 2. Step 3 is I'm going to decompose fs divided by gs as c times s plus a divided by s plus a squared plus b squared plus d times b divided by s plus a squared plus b squared. You basically can see the denominator will be the same. So you just split these two terms, okay? Just split them as c times s plus a and d times b. That's it. Okay. Let me not talk about how we do the inverse Laplace using the example. The reason why we do this form, okay? If we follow this step 1 and step 2 and step 3, then for this example we end up having fs over gs is 2 times s plus 1 plus 10. That's how we rewrite fs following step 2. Divide by s plus 1 squared plus 2 squared. That's we follow the step 1, rewrite gs, okay? And then for step 3, we decompose this one as 2 times s plus 1 divided by s plus 1 squared plus 2 squared, and 5 times 2 divided by s squared plus 2 squared. Okay, that's what we have for step 3. Okay, now we want to do the inverse. Okay, the inverse, if we do this inverse, it's just the inverse of individual component, basically, right? Okay, now before talking about how to do the inverse of this guy, I will show you some of this existing one. I'm going to use that one to figure out the inverse of these two terms. Okay, so if I remember, okay, in the previous, when we talk about the properties of the Laplace transform, I talk about the Laplace transform for cosine wt is s divided by s squared plus w squared. Okay, let's say this is fs, some function here. Okay, so also note L times EAT times FT is SA. So here Fs is L Ft. Okay, and I'll talk about why that's important. Okay, the reason this is true, the reason this second one is true, because let's do that. So if I rewrite f, okay, let's see, if I rewrite this guy as, because according to definition over here, right, f times sa, okay, sorry, let's write over here, let's write the first one over here. So the integration of the Laplace transform of e to the at times ft is the integration of 0 to infinity e minus, this is what I just copied the stuff over here, right, according to the definition of Laplace transform. Now if I put them together, the integration of 0 to infinity, so I can put these two together. Okay, let's hide a different, I put them together, so I have e to the minus s minus at ft, right? Okay, now let's do the comparison. Okay, so fs is integration of 0 to infinity e minus st times ft. Okay, so fsa is, I just replace the s, so this is s will be the equal, so s minus a just replace the s by s minus a, so it will be the same. Essentially these two will be equal. That's why L e minus EAT times ft is equal to fsa. Okay, all right, so now I show these two properties. Now I'm going to show you what's going to happen. Okay, now let's start with this first one. So the inverse of Laplace transform for this guy is just inverse of two different components, right? Okay, it's straightforward. According to the linear, this is a linear property of inverse Laplace transform. Okay, so now we have, so it's like the inverse. Of course, I use it's inverse of both. I can also put the two outside according to the homogeneity property. I can put all the scalar out. So I have 2 times L inverse s plus 1 divided by s plus 1 squared plus 2 squared. And also I can pull 5 outside. It's 5 L inverse. I leave the 2 over here. 2 divided by s plus 1 squared plus 2 squared. Okay. Now let's take a look at the first one. Okay. The first one. All right. So first one is kind of looks pretty complicated, but I can divide into 2 steps. First of all, let's do just the L inverse of s over s squared plus 2 squared. So the only difference is I sort of view this s plus 1 and s plus 1, I replace s plus 1 by s. Okay, this one we know how to do it according to this property, because the L of cosine wt is s divided s squared plus w squared, right? So your w here, if I take w is 2, right? So it's s plus s squared plus 2 squared, which is exactly this one. So its inverse will be just cosine 2t, basically. Okay, so I have here cosine 2t. Now I'm going to use the second property I mentioned over here. Okay, the property over here is L EAT is time ft is s plus a. Okay, now I already have over here. You sort of can see here, this is, if I view this one as this guy is as inside here, this is as fs. So I sort of want to have fs plus 1, right? Because I have to fs plus, I change s to s plus 1. I'm going to have this one, okay? So what I do is, hey, I'm going to have fs plus 1. According to here, fs plus 1 is inverse Laplace transform, is e atft, right? Because s plus 1 means I have e minus t, because a is negative 1. You can see view a as negative 1. So this will become f plus 1. So it's e minus t times ft. So which means if whatever get over here times e minus t. So I mean L inverse of s plus 1 divided by s1 plus 1 square plus 2 square is e minus t times cosine t. The reason I have e minus t because I change this guy, I change from fs to fs plus 1. So according to this property, I can say this inverse is e minus t times cosine 2t. Okay? So that's why I got the first one. The first one got 2 steps. I figured out, hey, the first one, it is 2 times e minus t times cosine 2t. Okay. Now I'm going to look at the second one. Is L inverse 5. I can ignore the 5, just whatever is scalar, right? I can look at the second one. Okay. So for the L inverse of 2 divided by s plus 1 squared plus 2 squared, okay, we can use the same property. What we do is, remember L sine wt is w divided by s squared plus w squared. Okay. And also I use this property, same property over here, is L E minus EAT FT is FSA. Okay, you basically also have 2 steps. Okay, if I only consider L inverse of 2 divided by s squared plus 2 squared, it just be sine 2t according to the first problem. This is the first problem here. You can get the first step. The second step, I just have to shift this s to s plus 1. Okay, which means if I'm going to assume this inside is the fs, so here I just have fs plus 1. Okay, so fs plus 1 is fs plus 1 is equal to L inverse. It's just equal to start over here. You say a is, if I let a to be negative 1. Okay, so here is negative 1. So I have the inverse L1 will be just e minus t times ft. Okay, ft already going here is sine t, because I already figured out this is sine t, so it's times sine t, sine 2t, sorry. Okay, so then I have here is L inverse, so I have L inverse of 2 divided by s plus 1 squared plus 2 squared is equal to e minus t times sine 2t. Okay, now I just replace this part by this. Now I figured out the inverse Laplace transform of fs over gs. Okay, alright. So one thing I want to emphasize over here is relation between inverse Laplace transform and Laplace transform. The reason here, it also means, okay, this means L inverse fs is, do it over here, s squared plus w squared is cosine wt. That's equivalent to this statement. This statement also says is L inverse fs minus a is EAT FT. Alright, so similarly here, this guy also implies the L inverse W s squared plus W squared is sine WT, and this guy also means L inverse F s minus A is EAT FT. Okay, right. Now I'll go over this example. Okay, this example only says I have 2 complex conjugate poles. What if, the next question, what if my GS has both real poles and complex conjugate poles? Assuming they are also distinct, which means the poles are different. The real poles are different, complex conjugate poles are different. What's going to happen? Okay, let me show you an example, see how we solve this problem. Okay, let's say I have y of s, which is 2s plus 10 divided by s times s squared plus 2s plus 5. So the only difference between this one and the previous one, I added one more s over here. So we have basically one more real pole. Okay, so here you can see this again as fs. So this is again as g sub s. So the poles, so first of all, we still have to compute the poles. So I'm not going to the details, very straightforward. So the poles, you just set the gs to be 0, right? And you solve for that, which gives us s times s squared plus 2s plus 5 set to be 0. The 3 poles are 1 and 0. The other 2 poles is plus 1, plus or minus 2i. So that's distinct poles. Okay. Alright, so here's how we do for the real poles. So for the real poles, distinct poles, what we do is we can still say we can decouple this one in this way. Okay, for the real poles, it still be written as A divided by S. For the complex conjugate poles, we can has BS plus C. So this one is different. We cannot just give a B over here. Okay, it has to be BS plus C. Okay, this one has to be less. So if this is my new F S, so this is degree of my F to the S is just equal to the degree of this is G to the S, G to the S minus 1. Basically, you can only assume that. You can also assume it is more than that. It's a degree minus 2, cannot be. So basically, you have 1 degree less than the denominator. Okay. So once we do that, of course, you can also say I have more distinct real poles. You can do this way. You can have similar poles as I mentioned for the same case for the first case. What if I have a more distributed complex conjugate poles? You can also have this one, many of this. Okay. Now, how do I determine this A? All these AIs. Okay, so AI we can use the same approach. So the A is given by FSGS times S, and let S equal to 0. So this is figure A. Or in general, you can do AI is Fs over GS times S plus lambda I, and let S equal to lambda minus lambda I. This is a way very simple. This is just case 1 that I described in the previous video. So how about this B and C's, or like B and CI's? Okay, so I don't have any method. You cannot use the same method over here. Don't use this method. It doesn't apply. We have to use the direct method. Okay, the direct method I mentioned in the previous video. See, this is the previous video. I talk about the direct method, which means, hey, I just assume I already know A, because you can figure out A over here, A value, whatever you already calculate over here. Assuming you don't know A, and you're trying to just plug in this B, assuming you have B and C, you don't know it. And what you do, you have to rewrite, you time both sides, but you make sure you select B and C such that they are equal. Okay, that's direct method I mentioned in the previous video. Okay. Okay, without going to this too abstract, I'm going to talk about example how we do that. Okay, so for the A, as I mentioned before, we only have one term over here because I only have one real pole. So you can see A is given by Fs times GS divided by GS times S, when S is equal to 0. So without doing, you follow all the computation stuff, you figure out A is just equal to 2. Okay, once you figure out that A is 2, as I mentioned, use the direct method, which is 2 divided by S plus BS plus C. I keep this B and C. I don't know what the values are. S squared plus 2S plus 5. And this guy will be should be equal to the original one, Fs over GS, right? So which means is this value. Now I multiply both sides by S times S squared plus 2S plus 5. Okay. I'm going to cancel out the denominator basically, okay? Once you do that, you just do this guy times this first one, you cancel out the S, the remaining term is this, okay? Don't forget we have 2 over here. The second one, you cancel out the second one, but you have S. We have BS plus C times S, okay? This guy, you cancel out everything, okay? You have 2S plus 10, basically. So you clear a little bit. So we have 2S squared plus 4S plus 10. That's the first one. The second one is the BS squared plus CS, which is 2S plus 10. The 10 will cancel out. So I have a clear out a little bit. So I have S squared, put them together, all the coefficients together. I have 2 plus B times S squared. I put for the S coefficient, I have 4 plus C times S, which should be equal to 2S, okay? Which means this coefficient must be 0, because I don't have an S squared term on the right hand side. So 2 plus B has to be equal to 0. So B is negative 2. And F4 plus C has to be equal to 2. So I have get C is also negative 2, okay? In other words, I have YS is equal to Fs over GS is 2 over S plus minus 2S plus minus 2 divided by S squared plus 2S plus 5. So if we do inverse Laplace transform, okay, the first term is fairly easy to figure out. It's just a step function, it's 2, okay? This guy, remember here, so only here, remember the poles are S squared plus 2S plus 5 to 0. So the poles are S is minus 1 plus minus 2I, basically, okay? So which means, hey, I have complex conjugate poles. So just follow the previous steps I mentioned over here. The step 1, step 2, step 3, and you want to use these 2 properties over here. Try to figure out this inverse Laplace transform. Basically, you should have cosine and sine somehow like this. You probably have some e to the something, right? E to the something t, e to the something t. Okay, follow the previous step. You can figure it. This way, how can address a general case when we have both real distinct poles and distinct complex conjugate poles.